那我们非常欢迎林丽琼院士来给我们介绍非常重要的一个材料能源相关的题目。我们欢迎林院士。
Good afternoon, everybody, and I hope just after lunch, this won't put you to sleep. I hope you enjoy it, and I would really be delighted to share with you my thought and also some of our research about part of a solution, perhaps, to save the world by reducing CO2. Okay. First of all, I will give you some very brief introduction on why we think solar fuel. Anyway, solar fuel is one of the possible venues that help us to reduce the carbon problem. And also, I like to say, as a material scientist, what I see is the challenges and opportunity for us to do something to make an impact to this problem. And I will utilize some of our research in recent years, in particular, focus on 2D materials, especially molybdisulfide, tungsten diselenide, tin disulfide, and even the graphite carbon nitride in general are in a big family of the 2D material. I'll show you actually step by step what we can do is just a binary, a simple material, what we can do to make it active. And also, in the long run, maybe there are more alternative ways to activate the material in the semiconductor wafer process. And in the powder paint coating solution, we can also do powder and during the process to make it active, productive, efficient to reduce the CO2. And also, I will show the last example of heterojunction, how that can help to boost the CO2 reduction. And all of these different approaches, I would like to share with you how, as a scientist, we can go by the atomistic surface design. In the atomic level, we can also see how we regulate the local chemical environment so as to boost the CO2 reduction efficiency. And of course, without powerful tool for us to probe and to understand the reaction mechanism, all the trial will be just blind trial. So I think we hope to have smart trial to improve the process and speed up the whole process to save the problem. Okay, so these are the main content. And let me start with the problem of CO2. And in the NASA's web, you can find such a graph telling us the global temperature anomalies since 1880. And year by year, you see the variations from region to region. Also, there is a fluctuation from region and region. So you can see not only the average temperature really is highly correlated, the increase highly correlated among the temperature and the carbon dioxide. But also the carbon, the region to region variation making some area which shouldn't be cold become very cold, or vice versa, which shouldn't be that hot become very hot. So these are really an issue to cause a lot of trouble in the earth. And as a matter of fact, this problem becomes more like a common consensus across all the world, okay? And this is a chart showing different countries. This is every country. They have set a goal that when do they want to reach net zero. And 2050 happened to be the year that most of the countries show their policies to make net zero at 2050. Taiwan is actually not on this map. because that's many problems we are encountering with the international community. We are not yet called a country, but Taiwan definitely can help, as we do for COVID-19. We show we can do to help the world, and Taiwan is actually helping. In our government, policy is announced in about 2 years ago that we have a grand plan. Okay, we have a goal also towards net zero in 2050. But in the intermediate state, at least we do have clear strategy to reduce the carbon emission to the 2030. So just 5-6 years now, we have to go to the low carbon energy. So these are clearly stated in our national policy. Now it's okay? Okay, good. Sorry, I didn't notice that. Just a quick quiz. Among the 100+ countries in the world, there are 2 countries now is already negative carbon. Which 2 countries? Anybody know? Huh? Iceland? No. Huh? No. 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 They are aggressively doing it, but they are not. Who knows the answer? I give you just one name. Maybe it was all of a sudden it will pop up why they will be the negative country. Bhutan? Yes, you're right. I should prepare a gift for you. I forgot. Bhutan, yes, Bhutan is one. The other one is a little bit more challenging. The other one. It's a small country in South America. Ooh, very difficult to get. Huh? No. Small country, yeah. No. No. The country name probably a lot of people have never heard of. Suriname. Nobody heard about this country. So it's just like a Bhutan, no industry. So it's a kind of country still very relaxed. And Bhutan, as a matter of fact, is the so-claimed the happiest country in the world, right? They have been ranked the so-called happiest country. There's no industry. They only have a lot of trees. So but anyway, I think their king has changed their mind. He wanted to develop the country. So let's see, 10 years from now, whether they can still maintain the negative carbon community. So it's worth paying attention to. But I wanted to say also, in Taiwan, there is a county very close to net zero. Which county? Any guess? Right, exactly. Nantou, of course, I mean, that's the only county, little industry, and lot of mountain and trees. Yeah. Alishan is not does not belong to Nantou. No, Nantou is correct. Nantou is perfect. Nantou is the only county. So if they plant more trees, they'll be there negative zero already. But so far it's still above. So anyway, but I just wanted to say, we probably don't want to go back to Formosa island, only tree, right? We are already too industrialized, so we cannot be negative zero by only planting the tree. So if it's only out of wishful thinking, and if it's only out of the statements, ambition, and their mission, sometimes it just doesn't work. Okay, so you got to have carrot and stick. Stick is also very important. And this is the stick that you have to be aware of. Now it's an international goal in 2026, especially from Europe first. The border tax will be started 2 years from now. Okay? And there is also the so-called RE100 policy. What does it mean? Okay. Let's say TSMC has they are the major supplier to Apple, Microsoft, and so on. But Apple already declared they want product produced with renewable energy, 100%. So 2 years or a couple of years from now, they are not going to buy any product from any company if they don't produce the product with 100% renewable energy. So TSMC should be nervous about that, right? And TSMC is already taking the actions. For instance, they are also part of the RE100, and they have already bought all the electricity potentially will be produced by our wind electricity. Taiwan has already maybe more than 100 wind power already for the last few years. It's a lot of effort, but if you don't do that, I'm sorry, if you don't do that, then TSMC cannot get any order from Apple. So it's a serious problem. So this kind of stick works. Now everybody has to really speed up in terms of paying the carbon fee, carbon tax now, okay? And then in the future, you have to push every product process into renewable energy. These are the data from Taiwan that where we emit the CO2 industry, okay? Actually, this number, close to 50% already, is due to the industry, okay? And of course, there are transportation, you drive the car, you emit CO2, and so on and so forth. But this is higher than the data in America. In America, this is about a quarter of the all contribution, okay? And transportation is also quite high in America. But Taiwan, just the industry alone, contribute almost half of that, okay? By sector, this is the number in Taiwan. But why CO2 emission is such a problem? It is because it is the main source of the greenhouse gas. Among all the greenhouse gas, okay, CH4, N2O, and so on and so forth, these only constitute less than 5%. More than 95% are from CO2. So this is really the problem causing warmer and warmer Earth, okay, and other things, of course. Now, let's look at the industrial problem. Why they emit so much carbon dioxide? On top of the list, the Formosa Petroleum Company, the China Steel, and the TSMC, and so on and so forth. They have the so-called category of Scope 1 is a direct CO2 emission, whereas Scope 2 is the indirect from the energy use, okay, they purchase. But then, nevertheless, if you add up all these, the biggest one, Formosa Petroleum, direct emission. Why they have such a big emission? This is Mailiao. Mailiao is the Liuqing. Liuqing is a part of the Formosa Petrochemical Corporation, and this was built at that time. It's also very historical and very important construction in Taiwan. initially, all these are just ocean, okay? So they built from the coastal area, extending the coastline to this far, and then the whole complex is as big as more than 2,000 hectares. Okay, in such a big area, they have to do the process relying heavily on the electricity. That's why they build their own power plant. So this particular power plant directly emit the CO2, and that's number one. Okay, so we enjoy the prosperity after Formosa company build these, but also pay the price. And overall, Taiwan, in terms of total emission, we are number 25 in the world. We are a small country, but we emit number 25. But per capita, if you divide by the number of the people here, we become number 22. So it's pretty high in the ranking of the world. China, for instance, they are number one in total emission, but they just have too many people, so become number 55. USA is number 2, and they become number 12 in the per capita. But no matter what, let's just focus on Taiwan, okay? In Taiwan, if you check all the individual power plant, Mailiao included here, okay? It's not for public use, just for their own. Number one is the Taichung power plant. When you go by the highway, when you pass by Dajia, you saw the big chimneys, right? Everybody saw it. Along the highway, you see the big chimney. And sometimes the big chimney does have a lot of almost look like a grayish color smoke. So that's really serious problem. And I did check just about a few weeks back. Even as of now, Taichung is still number one in the world. Just too big, way too big. So it's still number one. I think Taiwanese like to be number one in a lot of fields, but definitely not this one, okay? So let's try our best to make Taiwan also number one in terms of CO2 reduction. How about that? Instead of CO2 emission, CO2 reduction. We hope Taiwan can make to become world number one in a few years, okay? So, as I say, you do have to have stick. Okay. Carrot is difficult, but stick, it have to be there. And for the carbon tax, carbon fee are still currently under discussion. Our Minister of Environment, just about a few days ago, that he declared he wants to make to a conclusion in September. So let's watch only 2-3 months from now. Let's watch what's our decision on how much you have to pay. And this is a list from a lot of countries in Asia, okay? Some already put in place, and some is also about to do it. So this is the list, and we'll see what's the price we have to pay, okay? Yeah, and around the world, there are also a lot of countries, they already charge per ton of CO2 how much you have to pay. So Switzerland, Sweden, Finland, I think a lot of people have mentioned these very well advanced country. They charge pretty high, okay? Norway, Sweden, they all charge almost 180 or 100 US dollar per ton. Okay, so we'll see. I believe we'll probably just here because Taiwanese does not want to be charged too high, but we still have to charge something. Yeah. So about the national policy toward net zero, there are certainly a lot of strategy and a lot of policies implemented, and also there are many things that we can do starting from now towards 2050. If we wanted to reduce to 0, then if you only do linear progress by 2024 here, we're not there. By 2025, I don't think we'll be here either. In 2050, this will probably be mission impossible. But if it's mission impossible, should we just stop it or what? I think as long as we have a goal, if it's not 2050, perhaps it's just longer. How about 2060 or 2080 eventually? The young generation here, you will find out the way to go to 0, okay? But at least this is a general consensus how we can do it, okay? So first of all, now we already transitioned some of the coal-fired power plant to natural gas, okay? That's the first step. But natural gas only emit just half of the carbon. And then, of course, we can improve the practice in the gas-fired or coal-fired power plants, following the so-called CCUS. I will explain this later. But more importantly, we really have to increase and improve the use of renewable energy, okay? And hopefully by maybe a few decades from now, we can use 100% renewable energy. If not possible, at least we all follow the CCUS to get the renewable energy as effective and as low hazardous to us. Okay. Now for the renewable energy, here in this center, we also have a lot of projects relevant to the newer energy. I'm showing you also the data collected in Taiwan. Okay. The current status of the utilization of the renewable energy is only about 6%. Okay. And this is slowly increased in most of the renewable energy. Most rapidly increase is in the solar power. Solar power for the last 10, 12 years also. Okay, it's rapidly increasing, but still this is only constituted, if you multiply this by 6, just about 4% of all the power we use as of today. So we still have a long way to go. So we have to increase almost every part of that. We can't do much about hydroelectricity, but wind power is something Taiwan can do, and solar is also. I also wanted to make some side comment. Taiwan's trade between Taiwan and China, Taiwan's trade is either number 1 or number 2, the best wind fuel. Anybody know why? Why Taiwan's trade is so good in terms of putting wind power here? Terrain. Yes, correct. You're physicists, right? It's a good question for the general physics first year question. Okay. Yeah. But anyway, Taiwan is good in this, and in terms of the potential, we can really harvest a lot more energy from the wind. But of course, the construction cost is quite high, so that's why we're still trying to figure out how to pay it reasonably, but gain it maximized. Yeah. So, but in any case, I already see our construction of the over 100 windmill is quite impressive. In one of the daytime tests, we just turn on, it naturally turn on for the wind generated electricity. And for that one particular windy day, that alone can already provide the whole Taiwan. So that's quite impressive number that how wind power can make to us. Now, but it's all bought by TSMC. So, and for commodity use, we still have to build more. Yeah. And solar power, on solar power, in terms of the world map as of sunlight harvesting, Taiwan is not good. Okay, I don't have the map here, but if you check some of the it's also NASA or whoever, that in terms of the time duration of the sunlight and possible, Taiwan is so small. So if you times the photon input, if you times the total area, and you also have to remember, 3/5 of Taiwan land is occupied by high mountain. So if you wanted to build your solar panel, that's also not really very effective. So taking this all into account, Taiwan is not really the place to maximize the harvest of solar cell. But in terms of producing solar cell, then we are very good. It's part of semiconductor industry. So Taiwan can be just a good supplier for the world to produce solar cell panel, okay? So anyway, I think solar cell is also a very important project in this center. So if you can come up with more and more efficient and better way to harvest sunlight, even in the dim light or something like that, I think we can help. Yeah. So, okay. Now, as for the transition to the 2050 goal for net zero, our government has set 4 transition and 2 foundations. The 2 foundation technology is certainly what we can do, that every one of you are scientists, technologists. We can always find a place we can contribute, okay, to make net zero or even negative emission tech possible. So this is our charter. But then regulations on climate is something our government should do in align with the whole world, okay? But even for ordinary people, I'm sorry, I keep pushing the wrong button. Even for the ordinary people, we can have some behavioral change in our lifestyle, okay? Let me just take an example. Everybody use 3C product every day or even every moment. So whenever you click your computer or you use your iPhone, do you emit CO2? Indirectly, you do, okay? Because it costs a lot of electricity, and this electricity has to be coming from somewhere, maybe the power plant burning the coal, okay? So given an average behavior of Taiwanese, 8 hours usage of any 3C product is probably the number, right? Of 4 hours at minimum. You probably use 4 hours of that. So every time you use that, you already are participating in the CO2 emission. So should we just stop using it because of this? Of course not. We still wanted to enjoy the convenience of the 3C product bring us. So what should we do? As a scientist, you do have a lot to contribute. You can make whatever you're using to make it more energy efficient, okay? To make it, whatever, performance-wise, more efficient. So let me just take this as the example that energy-hungry things, if you can solve 10%, 20%, you're doing good. And this is also an example that I think some of you are also working on, is a LED. In the LED industry, if you look at the historical timeline, 30 or 40 years ago, we don't have LED to be a industry, okay? But nowadays, you can buy LED as your household lighting. Are these LED? Are these LED? Anybody know? Maybe you can demonstrate LED, and you can save money. Installation may be a little bit higher cost, but then at some year, and the endurance of the LED will pay you off. Okay, so these are the things one can do to change your lighting system, and then to utilize energy efficient household appliance. These are ordinary people one can do. Okay, change your lifestyle toward net zero. Okay, now let me come back to the issues of what we can do as a scientist, what we can do in the lab. Okay. To close the carbon cycle, there are many issues involving it. First of all, you can capture the CO2, you can use it, and then to turn into some product. So this will be the cycle we're talking about. How can we utilize that? Okay. And of course, each one of them all have their science and technologies. So some people can work on CO2 capture and so on. So let me just concentrate on one particular strategy to utilize the CO2. Okay. And this is a kind of new vision. The new vision is, instead of viewing CO2 as a devil, you view CO2 as a resource. So what CO2 can give us? Just use that as a source of carbon. So if you use CO2 and also water and shine the light, and then use some catalyst to accelerate the reaction, you can get either a fuel, low carbon fuel, or chemical feedstock. Okay, so this is an idea of utilizing CO2 as a resource. Okay, and this is killing two birds with one stone. Solve the energy problem and solve the environment problem. And the key here is the catalyst. Okay. And the catalyst, you have a lot to play. It's like a modern alchemist. The magic the alchemist can play with that. Okay, so for the photosynthesis, exactly they are doing CO2 plus water with sunshine. The tree can survive in their daily life. They only need glucose. Okay, they only need glucose, and that's exactly what they do. Change CO2 plus H2O into glucose. And this is naturally evolved with very deterministic process. Okay. The efficiency is low, but it's enough for the tree. They don't need much. But if for human being, we wanted to make an industry, 1% is certainly not useful at all. So we have to go beyond that. To go beyond that, we need to understand what it is involved. So usually, at least, I can break it into 5 steps. Number one is you need to CO2 absorption, and you also need photon absorption. So after you harvest the light, get to exciton diffusion and the separation, and then to the surface, they also need to get the charge transfer effectively with CO2. So with all these 5 processes, imagine you only have light absorption of 30%, okay? And you probably have absorption efficiency also just 50%. But exciton diffusion and separation maybe also 30%, or anything that you calculate. 30% times 20% times 10% maybe, and 50%, and then all of a sudden you drop down to at least 10 to minus 3 or even smaller. Okay? And in fact, if you just imagine this, a perfect crystal usually is inactive. Just imagine you are that CO2. Why you bother to come to a material surface to react. There's no incentive, right? CO2 is flying freely in the sky. They don't need to conduct, right? So you need to attract the CO2 to come to your surface. And this is not a trivial process for the semiconductor. And of course, when we start to think about what would be useful material, energetically, it also has to occur in such a manner the CO2 can reduce and the water can oxidize. And that requires the energetic criteria. So with these two alone, it's already a challenging process to select the right material. But then once you select the right material and then play with that, it is possible to further optimize that. And I wrote a review article with my former postdoc that we have summarized for the last few decades also all the material that has been developed towards photocatalysts. And there are quite many. So as a material scientist, it's really a playground that you can come up with different morphology, different material, and trying to construct in a three-dimensional manner to maximize all the possible CO2 capture and transformation. So it's really still an ongoing hard field. And if you look at the paper, I mean, the newer student, if you come study here after 2020, I think you have to read 3,000 papers. That's incredible. It's almost impossible to digest. But in any case, as long as you know enough concept, still find a place to work. We started this direction of research more than 10 years ago. Our first paper published in 2013. And over the years, always, it's just a matter of time. Each process, each particular issue, we try to adjust or got completed and published. So I'm quite happy. Some of them are actually highly cited paper. Now, I wanted to say, for the many, many different systems, now in my lab, we focus on three particular types: the transition metal disulfuride, and the graphitic carbon nitride, and a single atom catalyst. Because of the time limitation, I won't be able to cover a lot, but I like to focus on these two particular types and also show you with some selective cases to demonstrate how a material scientist can do to effectively boost the CO2 reduction. Okay, so the first example, 2D material, is actually a big family, a very large number of the 2D crystalline, and they have a different band gap ranging from near zero band gap to above 5 EV. But for maximizing the light harvesting and also producing suitable reduction in the oxidation to make it effective, this particular range will be more suitable, okay? Just balancing between light harvesting and energetical criteria. Okay. The 2D material does have their own beauties in terms of their form. They can have 1T structure, 2H, or 3R. Okay. The same MOS2 can all give you this type of phases, and they can be tunable from bulk to few layer or even to single layer. You can change the property from indirect to direct. I think that most of you probably understand from indirect to direct, the importance is to harvest the light even more efficiently. And because they are bound to be highly anisotropic, one can also play with these anisotropic factors. And this is just a theoretical calculation of many different 2D material with their bend position. Okay, so moly disulfide is not bad, and tungsten diselenide and tungsten disulfide, in terms of their bend position and bend gap, they are all in pretty good shape to begin with. And what one can play with is, I have to thank Ivan Huang's help to construct these nice figures. What we can do to play with these 2D photocatalysts, if they are perfect, as I mentioned, CO2 will not bother to react with you, okay? So you have to make something different. And one particular method is to generate defect. In this case, is sulfur vacancy by hydrogen plasma treatment. You just knock off the sulfur atoms. And you can also incorporate the hydra atoms, okay? You can incorporate by chemical base method or by ion implantation. And you can also build heterostructures layer by layers or with the chain effectively produced by utilizing different substrates. And maybe you can mix all these together. So the essence is to reach the atomic level manipulation and also control the interface by either by CVD method or by hydrothermal in the powder. Okay. So this is the end result of defect engineering in 2D material. And it does work in this sense that if you do only thin film, okay, if you do the gas product analysis by GC method, you'll see there are quite a lot of product, but they are all very small, almost within the error bars of detection limit. However, if you do sulfur vacancy modification by the hydrogen plasma, then all of a sudden, now you have at least 2 order of magnitude increase in one of the product. In this case, it illustrated it is the acetaldehyde. Acetaldehyde just shoot up, but then with the other products still maintain quite low. And if you do the heterostructure with MOS2 on top of graphene, you also see very effective boosting in terms of selective product. So this does work in the thin film case. And in the thin film case, I give you some quantum efficiency number here. This quantum efficiency number is calculated by the number electron transfer between CO2 to the hydrocarbon. Okay, so you can calculate all the number transferred, and then you divide that by the amount of photon you put in. Okay, so in this case, I should say this is apparent quantum efficiency, because if you have very thin layer, for instance, only single layer, you actually only absorb 3%, 4% of the light. Most of the light just goes through. So this apparently is an underestimated number because we assume all the photons that put in. But nevertheless, for the powder, you can use thick layer to maximize the light absorption. In this case, the apparent quantum efficiency for the tin disulfide with carbon interstitial that introduced in the hydrothermal process, we can have really also 2 order of magnitude compared to the undoped. Okay, so this is reaching 0.7% efficiency. So this is still among our top of the efficiency in our lab. So now why? I show you the result first. Now you must ask why they would have such a efficiency boosting. So first things, as I mentioned, CO2 has to come shake hands with your material. Okay, if it's too perfect, they just don't bother to shake hands. Now we create the vacancy by hydrogen plasma, and this can be directly observed by STM. Okay, without doing anything, the S produced in the CVD process you cannot get 100% perfect. You will also get some vacancy, but mostly they will be scattered single vacancy. So this is the single vacancy in the monolayer. Now, if you do plasma treatment, you will start to see clusters of vacancies. So you see, if you enlarge this, this is a few vacancy cluster. Okay. Now, the untreated, as presumably a perfect surface by calculation done by my colleague who is a theoretician. What he told us is CO2 just come as closest is 3 Armstrong. 3 Armstrong is not considered chemical bonding at all. It's mostly just physisorption if they do absorb, if they do stay, okay? And charge transfer is almost negligible. Now, with a single vacancy, the CO2 can come almost a little bit closer, but still 2 Armstrong away, and also very minimal charge transfer, okay? And scattered 3 vacancy, also similar, don't do anything. Now, you are talking if you have 3 vacancy cluster or even 5 vacancies. Now the CO2 start to shake hands with the material. With 5 vacancy, they really shake hands hard, okay? They have been bent in the bent form of CO2. This is called chemical bonding. And with all these, actually, you can see the the energy structure is already changed significantly from a larger band gap with a little bit more gap state, and more you do have change the band structure. Now, what does it happen? This is not cartoon, it's calculated, okay? So it's a simulation process of how CO2 come shake hands with MOS2 with 3 vacancy cluster or 5 vacancy cluster. Now they do shake hand hard, okay? So I talked about the basal plane behavior. Now, if we produce the layer in a sort of scattered island, under optical microscope, they are straight in the side, they are regular shape, but under TN, none of them are straight enough. They are always mountains and valleys, and if you analyze more carefully, you have the zigzag shape, you have the antenna shape, you have a lot of different reconstructed edges, okay? And the number density of the defect could be quite high at this level. So all these, they do have some formation energy. So apparently some of them are so easy to form the defect type as shown here. And more importantly, some of the configuration tend to attract CO2. Okay, if you focus on the one I circled with the purple color, the antenna, tungsten-based antenna, they have the binding energy quite high, which means they have more ability to attract CO2, and they do in such a way when CO2 come closer, they can capture it, okay, in terms of chemical bonding. So this is things we know we have low cost of forming such a defect, but then very easy, very favorable to do chemisorption of the bent CO2. And this indeed will boost their activity as illustrated by the scanning electrochemical microscope. Okay, this is a cistern half home built, and my former postdoc, now is also in Minzhi University of Science and Technology. She has spent a lot of time building this system, and we are now utilizing for all the systems we are studying. For instance, this is a sample of single layer tungsten diselenide. And under the AFM, you see the step, okay? So this is a step and very flat single layer. But then under the SECM, scanning electrochemical microscope, you can see at the edge, there's a big jump. In terms of current, you can collect it, showing higher activity compared to the basal plane. So this type of activity is edge promoted, and we can even calculate in terms of the size of the island. If it's too large, it's almost like a basal plane dominated and not really any enhancement. But then as you decrease the size, you have more and more edge contribution. And at 1 micron also, you can boost the IQE also by an order of magnitude and above. So this is very quantitative analysis of how edge can contribute. Now, edges is useful. Basal plane with defect engineering is also useful. However, both of them could have suffered from less stability. After a few rounds, maybe you lose the vacancy in the best optimized cluster shape, and maybe the edge also reconstructed in a more inert state. So this is a possible solution to replace the edge contribution of defect engineered surface. We do doping or alloy. So eventually, you want to create a surface, it's all fully connected. But then some of them are the heteroatoms. So this is the idea that initially I thought it is simple. We can start with what we do for molybdisulfide and introduce the third element. But it turned out my student kept telling me that she cannot find any vanadium. We tried to do vanadium doping. She cannot find vanadium after she did this. Okay, so eventually we find out we lose vanadium because there is a low melting temperature liquid form during the process, and they all evaporate. So this is not trivial at all. So she spent all her master thesis trying to fix the vanadium in. So we do capping. Okay, so this is a solution to keep some dopant in. But then, as a physicist, sometimes we are more brute force. Okay. If the material does not take the element, we implant it. By higher energy, we implant it. So implantation is a physicist solution. We just implant it, okay, by brute force. And we do both. So nowadays, I have some students doing this and some students doing that. Okay. This process is a common facility built in the National Central University, and we go there to pick the element they can provide and do implantation. So I'll show you just 2 examples of utilizing the VOS as usual by CVD, or we do CVD to produce binary, and then we do an implantation. So the doping and alloy is actually not just for the CO2 reduction. It does have a broader impact. Imagine this: silicon, gallium arsenide, gallium nitride, all the mature industry. If silicon does not have the capability to do doping, could you imagine? Will there be any device? No. Gallium nitride, the same thing. Gallium arsenide, all the same thing. If you cannot dope or alloy the semiconductor, there will be no industry at all. So same practice in the newer material like transition metal, dichalcogenide. This is still an early stage of development in the alloy and doping. So I hope what we learn here can be also practiced in a way for microelectronics and optoelectronics. Okay. Okay, so anyway, let me just show you quickly. But I saw my time is up. It's 5 minutes. So I have to fly. Okay. So now let me just show you vanadium alloy. It's also a surprise to us. Vanadium is not coming for free. They will also introduce vacancy in the same time. And then by my colleague's calculation, he ensured, yes, if you do vanadium, you will also have the vacancy. So we do have two effects coming together. So the energetic point of view that if we have higher vanadium, we actually, after 2% also, we can already have chemisorption. And this actually also help to reduce the barrier for the reduction of CO2. So this is a transient state, and the one with the vanadium of 4% actually reduce much so that this can occur, that they transform to CO. And this is the yield by the GC measurement. So indeed, we have about 5 times higher CO yield if you do the doping. Okay. And by implantation, we also see if we have maximized the dopant in such a manner, we can also increase by 3 times for this, in this case, it's methane. And this is the GC result. To understand what's really going on, we have tried a few different methods to learn what's really going on. So for this tin disulfide case, by the near ambient pressure SPS in the NSRC, what we learn here is with the dopant, we can increase the binding of CO, COO, and so on. So it effectively a direct evidence of the stronger chemical bonding of the material and the CO2. And also energetically, if you do without any doping, it's actually an endothermic process. However, if you do doping, you can make it into exothermic. So you can transform to an intermediate state, and this intermediate state, after a few more process, that we can get the end CH4. Okay, so these are all very helpful information. And I also like to say that all such study making material, utilizing spectroscopy, microscopy to understand in the atomic level is very important. And let's see quickly the graphitic carbon nitride that we make in such a case. This is by the chemist method is solution-based. So we start with the precursor with the melamine for the carbon nitride and adding boron, and then also adding gas bubbling agent to make very thin sheet, okay? And for the graphitic carbon nitride, we have difficulty to make good TM image, but we also have another powerful tool, the MMR tool. For utilizing MMR tool, we can specify where the boron goes, and proving incorporation of boron effectively. In this case, we proved it's in the base carbon. Okay, the stronger signal indicates the base carbon. The amino functionalization is very important in addition to the boron doping, because we can facilitate even more effective CO2 absorption. And the way we produce is highly porous. It's increased the diffusion channels, okay? And the nanosheet, very thin sheet, we also accelerate the charge separation process. We call it 4-in-1 modification to make carbon nitride more useful. And of course, my student can play even further with more doping. So the co-doping of phosphor and boron, and also utilizing two bubbling agents to make it even more porous. So I will show you just quickly. Besides the information I just showed you, we also rely heavily on the NSRC X-ray absorption near edge spectroscopy. With this technique, we can learn exactly once we do doping, once we make it into this form, we have on the basal plane, we have partial breaking, and interplane, we have stronger carbon-nitrogen interaction. So all these details can be analyzed. And I actually have edited a book just published early this year on application of X-ray spectroscopy in carbon dioxide reduction. It's one of the chapters my postdoc and I also wrote. So if you're interested, you can check this book. Maybe your library can have one book. So I think you don't recognize this is your data. Okay, so I also have to thank Yoron has provided the transient absorption spectroscopy to analyze our carbon nitride, and she told us that if we have the dopant, okay, in this case, okay, we can have, I think you can tell, it's a noisy spectrum, but still you can extrapolate reasonable number, and that give you direct evidence of a prolonged tau3 in the dope case. Okay, so thank you, and we need more. Okay, yeah. So you can do more, yeah. So because of the time limitation, I really have to fly, but just major observation on each slide in 30 seconds, okay? So actually, a lot of detail in material process does matter. This case, even when we made it into carbon nitride with different doping, but once we try to exfoliate the bulk form into the thin sheet form, the way of exfoliation also matter. And this is a case that I show you significant effect on the exfoliation. If it's thermally exfoliated, you increase the CO2 absorption, you increase the surface area, you increase every possibility to the active site, number of active sites. So this is reflecting in the final result of the thermally exfoliated one. You got 8 times improvement. Okay, very significant. So material scientist is important. How many of you want to become a material scientist? Raise your hand. Okay, it's so interesting. Just play with the material. Okay, yeah. So and not only for CO2 absorption, but also for liquid phase hydrogen evolution, you can see a dramatic 10 times improvement by the same technique. Okay, so what we are playing is really to make the local environment modulation and then to change the reaction pathway. Okay, this is what we do. Also, again, exothermic and endothermic. We doping without doping. So now I don't have time to talk about this. I'm sorry, but this is essentially play with the heterojunction charge separation. Okay, and light harvesting. Usually for the very good sample, sometimes it does not harvest light very efficiently. So we do have to have strong absorber, and for that, you couple with another, you can increase light harvesting in the same time, increase the charge separation. So this is the essential idea, and I don't have time to go through it, but just say that with combining the zinc sulfide and the zinc indium sulfide, we are able to produce a final result of 0.8 quantum efficiency. So this is by far the top material in my lab. Okay, yeah. I just need to tell you that the powerfulness of utilizing, setting up a lot of surface probing methodology to look at the reaction. And I also like to thank my colleagues, Wu Heng Liang in the CCMS. He has set up all these, and then in CCMS, me and Wu Heng Liang also have a few systems to look at the spectroscopic evidence of how the CO2 becomes some intermediate and become the final product. So we try to put together all this information to the story of the reaction mechanism. And sorry, I cannot go to the detail, but just to show you that now we are here, okay, and still struggling between 0.01 to 0.1%. And if I have to say that commercialization, maybe they are looking for 10% and above, okay, but we are not there yet. But I hope some year from now, we can achieve a few percent at least. So I'm not giving it up, but I'm just saying that we are still far away from commercialization. And now we are looking at ways to improve all the metal sulfide and the carbon nitride. Okay, so this is my last slide, and sorry to keep you this long, but I hope you find a good research opportunity, and you also get excited how much you can contribute in the future. Yeah, and I like to quote Richard Smalley's slogan in his later life. He always say, "Be a scientist, save the world." And we are privileged to be a scientist. We can save the world. Okay. Okay. And I have to thank all my group members here. They do a lot of things for me to stand here. So, yeah, and also my collaborator. And there are more collaborators. I just don't have time to go through all the names. And sorry if I didn't mention your name. Yeah. Okay, thank you.